Okay, we're almost at 7:30. If folks could start taking their seats, please, we'll get the meeting underway. Okay, it's 7:30 and I will call the meeting to order. I'm Jay Lavender. I am the president of the Edmonton RASC, and I will be your host for tonight's meeting. As usual, we have a couple of housekeeping items to get through, and then we will get on to our guest speaker. Firstly, our October 7th meeting minutes have been drafted and posted on the OneDrive. Are there any questions, errors, omissions, anything for those meeting minutes from anyone? All right, hearing none, I will pass the microphone to our secretary.
I moved that the October 7 meeting minutes be approved as posted on the OneDrive.
Thank you, Daisy. And we have Dave as the seconder. Do we have any discussion? All right, for all the members, all those in favor of the motion, please raise your hand. Any opposed? All right, minute motion is carried. Thank you. Okay, well, let's get on to our guest presenter here. So, our presenter is currently an assistant professor at University of Alberta. His research is primarily focused on classical and quantum gravity, black holes, cosmology, and quantum field theory. He did his PhD in quantum gravity in Uruguay under the supervision of Rodolfo Gambini, a world leader in loop quantum gravity and black holes. He has held a postdoctoral position at the Metropolitan Autonomous University and also at National Autonomous University of Mexico. And prior to his current position, he was an assistant professor at York University in Toronto and an assistant professor at Monterrey Institute of Technology in Mexico. Please join me in welcoming Dr. Saeed Rastgoo. I'll try to get your thing going here. All right, there you go. There's your clicker there.
Okay, thank you very much for the warm welcome. And also, I'm happy to be here among, I suspect, many fellow amateur astronomers. I'm myself, we have a telescope 9.25-inch EVO at home. So maybe at some time we join you. I saw some of the events that you have here. So yes, so my So my talk is about, as you see, black holes tonight, and I want to get you the picture actually on the forefront of research in black holes, how we use a certain diagram of a space-time to understand black holes. So you have probably seen a lot of documentaries from Brian Greene, from other people about black holes. So they have this spatial, like just a space cartoonish view of black holes, and it's very nice, but I'm sure that you're fed up with all of those. So you want to know a little bit more detail about what really happens in a space-time of black holes. So I want to introduce you in that diagram, this diagram that we use to study black holes. Okay, so if I click here, maybe I do this. I'm not sure I can. Oh, here. There we go. Okay, so we start with our friend Alice in space-time. So because Alice lived in Wonderland, in physics, we usually use Alice for our presentations. So just to mention that she is not living in space, just space, but in space-time. And this is very important for our talk, for my talk. So this is Alice. She's actually not a 3D person. That's why she's kind of jealous of us being 3D. And she lives in a one-dimensional space. And this space is called Wonderland, but this dimension. So we want to get her help to, introduce us to this concept of space and time, together space time. So she lives here near a blue planet. There's some space station to the left, some planet to the right. And so she has this routine that she wakes up at 8 a.m. and then she travels to the red planet, arrives there at 9 a.m., does a few things there until 10 a.m. and then gets back to the blue planet at 11 a.m. Now you see that this is not very useful if you have just this picture of a space. If you have animation, it works, but usually we have just snapshots of the life of these objects. It's not useful. So if I want to make it this picture more useful, you see that I can draw these vertical lines, and whenever it cuts the blue space, it says that intersection is 1 kilometer, for example, from the blue planet, and then this is 2 kilometers, this is 3. These units could be million kilometers, it really doesn't matter, 4 and 5. Okay, so yes. So, okay, now Alice is not happy with how I represent her life. So let's do a space-time diagram instead of a space diagram. Probably the easiest way you can think of that is that just to present snapshots of motion of Alice. So this is at 8 a.m. You see here, you cannot see my mouse here, but maybe, yes, 8 a.m. here. And so, well, that's a snapshot of her location. Then we have 9 a.m. here. You see again the time there. And she's at the red planet. And 10 a.m. she's still at the red planet. And 11 a.m. she's back. Okay, very good. So we have some sort of now everything at the same time. Now you can see how she moves in space and time. And so I can say that I have this direction to the horizontal direction as a space at each layer. So I see that time goes kind of up in this picture. Now let's get this time there. So there's a blue axis here that represents time. It goes time, so we can see the whole life of Alice in these 3-4 hours. This is called the space-time diagram because you can see each position of Alice in each time. And then let's remove all of those layers, represent them by some abstract layer. So this is every point on this line. This is a space at all the space at 9 a.m., all the space at 10 a.m. So here is some point of a space at 10 a.m. Here is some point of a space in 11 a.m. So you see that this is the kind of represent a space and time at the same time. Now, if I also draw these vertical lines, you see that these vertical lines correspond to when they hit this blue axis. This is 1 kilometer, 2 kilometers, 3 kilometers, and there's -1 kilometer, basically means to the left, -2, -3, and 8 a.m., 9 a.m., 10 a.m. goes up. So let's go forward and rename these things instead of kilometers just to units, 1, 2, 3, whatever, million kilometers or whatever unit you want. Here also 1, 2, 3 from 0. 0 means present. Okay, now remove these. Before removing these, let's put Alice where she was. So she was at time 0, she was at position 0, let's say, right, near the blue planet. Then she moved to another location close to the other planet at 1 unit of time up. So this is this 1 unit of up, and she's now at unit 1 in space. And she stayed there for 1 unit of time. And then she came back to original position. Now I remove, actually I connect these lines of Alice, basically position and time, and then I remove Alice. So you can forget about Alice. It's just the whole life of Alice in these 3-4 hours is just here, right? Goes up in time. So everything goes up in time, of course. Oh, my mouse is here, good. So everything goes up in time, right? Nothing can stay in time or go backward. So everything goes up. At the same time, you can go left and right, right? So Alice goes to the right, stays here, and goes to the left. Very good. Now let's remove all of these things here. Just leave a space axis and time axis. And this is what we call in physics a space-time diagram or word line of Alice, right? Very nice. So we know how Alice moves in space and time. And next, let's put the planet there. So this is another blue planet, not that original one. This also is staying here and not moving. So you see the word line of this planet is just one straight line up. It should move upwards because everything moves towards forward in time, basically. So everything moves upward in this picture. But the planet doesn't move left or right. Okay. Now, the next thing is to see, for example, you can ask nice, very important questions using these diagrams. For example, what was the position or what was the time when Alice was at 0.5, let's say, kilometers or whatever distance you want? So you just connect this 0.5 kilometers, and whenever it cuts the Alice's word line, you see what time it was. So it is 2. Okay, so she was 0.5 to the right at 2. Another question, for example, she was at 1.5 at 5 hours after the, starting her journey. And she moved a little bit up in time and also left. And so you see that there are 2 times actually that she was at 1 kilometer. So she went first towards right and she was here and then stayed here and came back. So this is all the information about the whole lifetime of everything, including Alice, but whole lifetime, I mean just 4 hours or whatever. In this case, is here. The same for the planet. So planet also stayed here, all the time stayed there. So you can see the whole universe basically in this way in all the times here. So this line represents the whole universe where Alice lives, Wonderland, at 3 a.m., for example. This line represents the whole universe at 6 a.m. So any point on this is a galaxy, is Alice, is a planet. So that's, but also you can see the whole time. Everything here is a space and time. So this is called the block universe in Einstein's language. Everything is there, right? Okay, next, you might ask, was Alice ever at 4 kilometers, 4 light years, whatever distance from the center? No, you see that this white line never cuts Alice's fourth line. So Alice was never here, obviously. She never reached this position. Okay, so these are some basic things we learned about the spacetime. Now we know what is an spacetime diagram. Let's go to causality. And you will see that causality in physics is really, really related, I mean, completely related to how light moves. Because light is the fastest thing we can use to, pass on information, send information. So, okay, let's get again. Alice here, this green word line. Here is the planet there. Now, what happens is I'm going to ask Alice to send a flashlight signal, that yellow thing that you see there, to the planet to the right, while she moves upward in time, forward in time, and also moves right and then stays there and goes left. She also sends this flashlight signal. Okay, so that's next time Alice, the green dot, moves a little bit to the right on her diagram, space-time diagram. That yellow thing is the flashlight, one single basically signal of flashlight. And the planet is also not moving around left or right, it's just more going upwards in time. Next, you can guess what happens. So the flashlight, the light, the yellow thing is moving much faster than Alice, faster than anything else. So it's, you see, going faster to the right than Alice. This continues until, as you see, the signal from the flashlight reaches closer and closer to the red planet on the right. One more step. And finally, the light is there. You see that nothing immediately affects the red planet. So the signal doesn't obviously reach the red planet immediately. It takes some time. And that time is from here, this time 0, all the way to this time, whatever time it took. This is the fastest time they can communicate, basically, Alice and the planet. So what is the trajectory of light, word line of light? Just take all of these steps that I plotted before and connect them together. Draw a line between them, forget about those dots. And this is the light, the word line of light. And something interesting is that the world line of light or space-time trajectory of light is always the same because it doesn't change its speed. The speed is always the same, speed of light. And so this is when light goes to the right. And then Alice could also send a signal to the left, right? Again, light goes to the left, right? But also everything, including light, should move forward in time. So it goes left and up, left and up, left and up. And that's how you imagine that, word line of light. Okay, why is this important? Because, as I said, this is the fastest you can travel or send signal, but also there's something interesting here. If you look at this and imagine this, if a space instead of one-dimensional was two-dimensional, you would get a cone here. This is imagining this space is two-dimensional, so it's a cone. And this is called the light cone. And this is extremely important in physics, in gravity especially, as you will see in a minute why. So when I say future light cone, it means that basically the trajectory of light going everywhere, light and left, when it goes upwards towards future, basically that's the light cone. Very nice. So you will have this sort of light cones everywhere in space-time. So this is the full space-time. As you remember, this is the whole universe at all times, at all places, right? So for example, Alice is here. This is the future light cone, her future light cone there. Suppose that there was a Bob here, a future light cone of Bob, another object, and so on. Okay, so imagine Alice here, let's say this is Alice. Imagine Alice could send light signals also backward in time, right? The speed of the light is still the same. It just goes backward in time, which no one can do, but let's say Alice could. And this would look like that, right, to the left. And if she could send a signal backwards in time to the right, that would also be that, right? Now, although we can't do this, you can send signals to backward in time. But what happens is that if there was some other Alice prime, like Bob, someone else, would send light signal towards Alice, towards right? So this is Bob, this is Alice here at that time, previous time. So the light signal is going towards right, but it also should go up in times, right? So this is the light signal that comes from someone here to the left of Alice, sending light to her. So there she receives it there, a little bit to the future. The same way, if there was someone to the right of Alice at that time, so Alice was here, Bob was here, the signal was sent. Of course, it doesn't go like this because it takes some time. It should go forward in time and reaches Alice. Now, you see that Alice now has two light cones. This is the top one. We already saw that it was future light cone. So all the lights that go away or emitted from Alice's flashlight to the right and left and go forward in time, that's that. And you have the ones that are reached to Alice from past, and that's called the past light cone. Okay, so next I want to see what happens. So what we saw that what happens if we have a light signal going to the right or left. Now let's say Alice, in addition to sending the flashlight signal to right, for example, at the same time she also throws a ball towards the red planet, right? But this ball, of course, goes slower than the speed of light, like anything else that is not light. So this is the pink thing here is the ball that she throws there, and let's see how it moves. Again, further in time, Alice is the green, goes up in, all of them go up in time in the same rate, but Alice moves a little bit slower than the ball a little bit slower than light, and this continues. So you see how all of them are moving in a space-time. And as you see, of course, light is faster than all of these. Light reaches the red planet faster than the ball. But my point here after this is to plot the trajectory of the ball and compare it to the trajectory of light. So there you go. The ball is still not reached the red planet, obviously, because it's slower, but you can see it very clearly in the space-time diagram here. So what was the trajectory of the ball? This is the trajectory of the ball. As always, we connect these and compare it to the trajectory of light. So this is a simple diagram, but you can read many things from it. First of all, this distance, the vertical distance from here to here, this represents the time that light took to reach to the red planet from Alice when she emitted it here. But the time, this distance is the time that took for the ball to reach Alice, from Alice to the planet, right? It's longer. You can clearly see why everything happens in a space-time in that way. And the universe, in this universe, is not nothing is changing, right? So if you have some vertical thing that goes up, tells you that is now, that is now, that is now. If you think about this, all our life is already in that space-time. It's already depicted. It's there. You're just going forward in time and experiencing those moments, basically. But everything is already there in this picture. This is also the left light, part of the light cone as you see it. Now, let's put small light cones everywhere here. We will discover something very interesting. Let's put this future light cone on trajectory of Alice in several places. Here, okay, you see that the green line is inside the light cone. How about this? Again, inside the light cone. How about this? Inside the light cone. Inside the light cone. This ball, was it traveling faster than the speed of light? No, it's slower. Is the trajectory pink one inside the light cone? Yes, everywhere inside the light cone. Very nice. How about the planet? Is not moving, which means that this is going slower than the speed of light inside the light cone. How about the light? Oop, this is different now. Light moves on the light cone, exactly on the light cone. You see here or the other side, all of them on the light cone. So before going forward to, so you see all the light cones, I plotted them here. You can also put the past light cones everywhere. Yes, you see the objects that move slower than the speed of light, their trajectory is always inside the light cone, either in the past light cone or the future light cone. So past, future, the line is inside the light cone here. For light, either past or future, everything is on the light cone, which makes sense because it's a light cone. Okay, so you might ask, is there anything that is not inside or on the light cone or outside the light cone, basically? Yes, but that's not physical, as we will see. So that's the question. Everything outside the light cone. Let's again do another experiment. Now, Alice has a magic ball that can go faster than the speed of light and see what happens there. Okay, so the trajectory, all that story again. Now the light is slower. The yellow signal is slower than the blue signal, which is the ball that goes faster than the speed of light, moving forward in time. And to the right, all of these objects except the planet that just doesn't move left or right, but moves forward in time. And the ball that goes faster than the speed of light reaches, of course, faster than light to the planet. Again, plotting the trajectories, connect these points, and compare it to the trajectory of light. Okay, now let's compare the light cones. You see, the ones that move slower than the speed of light, the trajectory is inside the light cone. The ones that go with the speed of light, which is light itself, the trajectory is on the light cone. Anything that moves faster than the speed of light is outside of the light cone. So light cones create three basically category of objects. Slower than the speed of light inside the light cone, on the light cone with the speed of light, traveling with the speed of light, and outside of the light cone faster than the speed of light. So we can never in the universe have anything that goes outside of a light cone, right? Otherwise, I mean, we would not have relativity. Good. Now we know everything about all of these. So the next thing is about basically some consequences of this. Suppose that this is Alice again, this is a galaxy, and this line represents, this doesn't mean that Alice is always here. It just means that this line represents Alice's world line. She's not moving left to the left or right, sitting here, doing nothing, just going forward in time. There's another galaxy also sitting there doing nothing, going up in time. And there is 1 million light years distance between these two objects, right? Now, if suppose that at this point in time, so all the universe, right, all the one-dimensional universe is here at this point in time, let's say, I don't know, 1 million years ago, 10 million years ago, and this galaxy is sitting at this position at that time, and Alice is here. If the galaxy is just formed and sends us the first light from its formation, right? So that light takes, as you saw, goes on a light ray trajectory to reach us. That light does not reach us until 1 million years. That's why the light, but why we see objects in their past way, like how they were in the past. Suppose that there's another galaxy at the same time here, sitting a little bit farther, 2 million light years. And again, it's formed exactly at that time. And then when it's formed, it sends us the light. And after 1 million years, the trajectory of light, you remember, is always the same. Where is it? Here. It's not reached us yet. It just reached this first galaxy, barely passed it, but not reached us. So we haven't seen it yet. There are things that we haven't seen at that time. We have to wait until here, 2 million years. So after 2 million years, suddenly we see something in the sky, the new thing in the sky. We couldn't see 2 million light years away from us before, right? Oops, here. Until here, we couldn't see it. When we reached here at time, now we could see farther. So that's why they say, when you look farther, you also are looking further back in time. That's all because the speed of light is limited, and that's the speed of light is the fastest speed anything can move in the universe. So you have to wait until this actually reaches your trajectory here, so you are able to see that. Now, something even more interesting. Suppose that there was another planet here. Okay, so suppose that now this is our present time, right? This was our past, all of them. Now this is the present time universe, and we are here at this point in space, at this point at time. Now suppose that there was a galaxy there more than 2 million light years away from us. So it is around, let's say, 10 million light years, whatever. This is not too scale. It was formed here, and it's sending light towards us, right? And after 2 million years, where is the light? After 2 million years, this distance from here to here, this is 2 million years. This is here. We haven't seen it yet, obviously. This is our present. So although the galaxy is there, at the present, we can't see it, right? It takes another, let's say, 2 million years from present. So we can, oops, let's go back. So we can see that there. So we can see it there, which is not present. It's in our future. This is what they call cosmic horizon. It's different from black hole horizon. Cosmic horizon for us now is this pink line. Everything closer than to us, we can see that because this light has reached us before or now. Everything after that, we haven't seen it, although they are there. That's why they say that they have this term of observable universe. Observable universe is what we can observe now. Maybe universe is 20 times larger. Who knows? We see farther and farther when time passes more and more, right? So that's the thing that's about the universe. We can never really see as much as we want. One more thing is that about this light cones is that suppose that you're here, right? Oops, this is you. You see that you can only see light, right? To see everything by light, but light only travels from your past light cone to you, right? So everything you're seeing in your life is coming from your past light cone. So you're seeing me, but actually what you're seeing is me a millionth or 1,000 millionth of second before. You never see anything at the present moment. Everything you see is on your past light cone. So the farther you look, the farther back in time you look, right? Because I'm very close to you, you don't really notice that I'm in your past. But when we really look farther, we see that the objects are really to our past. So this is very interesting. You never see anything at the present. Also, so other lights just pass above you or below you. You have already seen them or don't affect you. Another thing is that if it goes forward, I can Okay. Is nothing can affect you at the moment, right? So if you're here, if you're here, and there are two objects to your left or right, one of them is a Jedi, the other one is Yoda, I don't know, whatever. And they want to attack you, right? I'm really not a Star Wars person, but I'm trying to be, to appeal to the Star Wars people. So it is these objects, you think that immediately they can affect you. No, it's not possible. The fastest way they can affect you is to send some signal, laser gun, whatever, shoot you with a laser gun. But that laser is a light. It takes some time they reach you, right? You're safe until you don't go forward in time, right? But you cannot stop going forward in time, unfortunately. So you're not completely safe. So when you go forward, actually the light hits you, right? Also, the next slide. So you can never get affected or affect anything at the present state of the universe. So let's say this is the universe at present. You not only don't know what is around you at the moment exactly, because you have to wait for the light to reach you, you can also not affect anything, or anything can affect you at that time. So we are really living in the past. Everything is happening in our past. Okay, now let's get to the third part of the talk. Hopefully I'm not too late. So we have these causal diagrams. After that, we go to the black holes quickly. These are called Penrose diagrams. So I'm introducing something to you that is actually used in actual spearheading of the research, but without any mathematical formula, hopefully. So let's take, again, this is space-time, this is time, this is the space, and all the light rays that go towards right, remember all the rays were going like that, light rays, and all the light rays in the universe that go towards left, right? Left means that they go left, and also they go forward in time, so they would be sloped like this. Now, in the next step, what I'm going to do is to put a boundary around them. So this boundary, or these boundaries, is this line is where all the light years that are going to future and towards right end up. Some were very, very far from us, but they end up here, all of them. In the same way, this, maybe actually I have. Yes, there you go. So this is all the light years that, all the light rays that go towards right end up here. The same way, all the light rays that go towards left, and of course go forward in time, all of them end up on this surface, right? This is very far from us, but I brought it close just to so you see that. What is this surface? This is the surface that all the light years that came, basically go towards right, came from. All of the light that's coming from towards left comes from this surface, right? And in the same way, all the light years that go towards right were here at some old time, infinite time ago. You couldn't say Big Bang. Now, let's put the space-time there and forget about those light rays. These boundaries are very important for us. This looks very simple, but it's very important, as you see there. 8 regions in this diagram, very simple diamond, right? On top, that red point on top, red point at the bottom, red point on the right, red point on the left, and 1 side, 2 sides, 3 sides, and 4 sides. What these are is very important. So these 4 sides I told you, so all the lights going to left and right end of these and originate from these two. You saw that. How about those points? So that point on top of that is actually not a point. It's a surface. It's a vertical surface, but with our twisted mathematics, it now looks like a point, but it's very far from us. That's why it looks like a point. It's actually a surface. That is where all the objects that move slower than the speed of light end up. So all the lights end up here to the right or to the left, but everything that is like Alice, Bob, but whoever, us, end up here. And that thing in future, very far in future, and that's actually a surface like this, horizontal surface. But again, it's very far, so it looks like a point. The same goes here. So everything that actually universe started from there, basically, everything that has mass started there. So it's still not a point, it's a surface. Again, this is our mathematics that makes it look like that. And those 2 points. The right point is if you really take Alice and put Alice all the way to infinity to the right, at any point in time in her life, you end up there. Again, that is not a point, it's a surface, vertical surface now, because you have different points in time, but it looks like a point because it's very far from us. The same way on the left. So if you put any object, take any objects that has mass and push it to the left up to infinity, you get that position. Again, that's also a surface. You see, there's a lot of information in this simple diagram. Now, Alice, or any object with mass, looks like this, goes up in time, goes left or right, up in time, left or right, all the time, and starts from very long in the past and very far into the future, assuming that this object lives forever. So if it lives forever, you can do that. And if I plot these light cones, you see that this object is massive, or has mass, so cannot go faster than the speed of light or equal to the speed of light. So always this green line is inside the light cone. Very nice. Now, you know that? Now let's go to black holes. Okay, so this is the heart of the talk. So if you have a space-time, remember the space-time was just this yellow thing around, right? And everything inside was also objects moving around. Now, if you put a black hole in space, something very weird happens. First of all, two lines that look like light rays happen here, but they are not light rays, as we will see in a moment. Second, the top and bottom, so you see these curly lines, these appear here. I will explain what those are. And those top ones are gone away, right? So this is very strange now. What are these things? So there are two, okay, let's enlarge this picture. So there are two things, one green thing on the top, this curly thing on the bottom, then this green line, another green line, this green line, that green line. And there are three regions, region 1, region 2, region 3, region 4, right? I just cut the top and bottom and put some curly lines there. I didn't do, black hole did that. Okay, so this on the region, in region 1, that was where you saw Alice could move on, and there's everything going on very nice from very long time ago to very long time in the future, all good as before. However, something happens here. If this object, this Alice, for example, moves in this way, moves here and passes this point, passes this line. Okay, so she ends up here. Okay, there's something interesting about this here. Interesting thing is that if you draw the light cones like the light that is emitted by Alice here, to the left or to the right, all the lights, when you're inside this region, triangular region, end up in this curly red thing, right? You can never come out of this region that has a boundary of this pink, basically dotted line. Once you are inside, that's it. You can never get out, because the fastest you can move is the speed of light, right? If you are light, you move this. Even if you're here, you move with the speed of light, you don't get out. You just hit this red thing here. You're trapped there. That's it. Another point inside, you're trapped. Nothing can get out of this here also, right? Even if you're very close, as I said, very close to this boundary, still you cannot get out. You until end up in that. So there's no way. The only way that you can get out is, what do? You just go this way, right? Like this way, or you go that way. But remember, that line is outside of the light cone, which means that you have to go faster than the speed of light. We can't. If you don't go faster than the speed of light, you're trapped in this triangle. And that triangle is called the black hole, because you're trapped there. Nothing can come out. It's black. The light also cannot come out. What is this line? That is called the horizon, because nothing can come out of that, right? This is the horizon. When you pass it, that's it. You're doomed. You're there. This is called the right horizon of the black hole, and this is called the left horizon of the black hole. Okay, so what is the thing that is up there? That thing up there, remember, everything would end up there. Once you're inside the black hole, you end up there, because you have to go forward in time, and you end up there. And that is some weird place. Actually, it's not a place, it's when. This is called the black hole singularity. And this singularity is not somewhere. It is some time. This is like death. It happens to all of us. It's not somewhere. It's just all of us hit that at some point. This region is called the right exterior. So it's outside of the black hole. This is exterior. There are two exteriors. That's very weird. One to the left, one to the right. So this is universe 2. There are 2 universes in this diagram. And if you're inside this triangle, you can never stay inside. Whatever you do, you just will be spat out here. Anywhere here, you cannot stay because you have to go forward in time. And forward in time, you always end up outside, right? And that's why it's called, so nothing can stay inside there. And it's called the white hole. Everything comes out of there. There's no way. This is inverse of black hole. It doesn't accept you to stay there. And so this is called the singularity of the white hole. And this is the right horizon of the white hole, left horizon of the white hole, all of that. So this is the picture. White hole, black hole, exterior 1, exterior 2, 2 universes that are outside. Now, something interesting is that if you are outside the black hole, you can end up in the black hole. You can just go forever outside of the black hole. Very nice. This way, falling into the black hole. The same happens for the other part of the universe. You can always go to the black hole or away from the black hole. However, you cannot get ever from this universe to that universe. These are completely causally disconnected. Absolutely, you have no information about that, right? You see that if I want to go from this exterior, this space-time, towards that exterior outside of this, so there are 2 outside of the black hole, I have to move on a trajectory like this. This is outside of the light. A speed of light prohibits you to do that. You have to go faster than the speed of light. So these 2 universes, although they both exist, there's no way you can access or send any signal towards each other. They're completely causally disconnected. Yes. And so, but if you're in a white hole, you can choose which universe you go. Go to the exterior 1 or exterior 2. You can choose that. There's no problem with that. There's something in between these 2 black holes and white holes. So the horizons match there. It's called a wormhole. You have heard about that. And this wormhole, if you draw the light cone, it looks like this, right? Okay. So how much do I have?
Oh, you're fine.
Okay, good. Okay, so let's look at this black hole again. There are more interesting things you can see from this humble diagram than you can imagine. So take all the light years from the universe, history of the universe that they fall inside the black hole. So if you can catch all of these light years, look at all of them, you see everything that happened in the universe, right? So something happens here, that light goes inside. Something happens here, that light eventually goes inside. All the history of the universe contained in these light rays. They all fall into the black hole. Also from the other universe, right? But imagine, look at this. If you are here, you can never see these light rays. They are inside. You can see them if you're inside the black hole, but never they reach here because you need faster than the speed of light thing to reach from left to right. Okay, so remember I said that this is infinite to the past outside the black hole. These 2, one to the left, one to the right, these 2 points. And also I said before that those top points here and there, they're infinite to the future outside of the black hole and white hole. Okay, so let's take Bob. Bob is starting from here. Very nice. Takes some, trajectory, lives forever, of course, goes from minus infinity time to plus infinity time. And this is word line of Bob. Now, suppose we have Alice. Alice is a daredevil, so she tries to go inside the black hole, right? So she goes inside the black hole. Here, she's doomed. She ends up in singularity. Okay. But what happens here? Something interesting. The time, so this is like maybe 4/5 of the history of the universe, right? From here to here. All the light years from this light year, this, all the events happening in this region, Bob can see them. Why? Because Bob is here, sees the event, the light emitted from the event here to here, sees it here. Another event happens here, Bob sees it. So everything that happens here, Bob sees it, right? 4/5 of the universe. But it takes this long time, this distance. You see here, this Takes this amount of time. How about Alice? Alice, to see that exactly those light years, all of those. So, for example, this first light ray ends up here. Maybe this one ends up here, and all of it. So it takes much less time for Alice to see all of that history, that's 4/5 of the history of the universe, much less. And so this shows a few things to you. If you fall into the black hole, you can see the universe actually faster, or basically the universe goes faster for you. So as I mentioned, so Alice can see this history in a shorter time. This means that the outside universe, when you fall into the black hole, it speeds up for you. You see everything. Why is everything happening so fast now outside? I will show a quick animation or movie actually, but that's what happens there. So you see now how actually what happens. But Alice pays a price because all those lights are coming towards you in a smaller amount of time. So this is a fixed amount of energy, but coming towards you in a smaller amount of time. So the density of energy per time is higher. So that is called the blue shifted light. It's very energetic compared to what Bob gets, right? So Bob gets all those lights in much more longer time. So this means that unfortunately, Alice will burn before seeing all those things. But she knew that, right? She was a physicist. So anyway. Also, let's see another Alice, Alice 2. Right? And this Alice is now moving inside the black hole, right? But going this way, of course, ends up in the singularity. However, something interesting happens. When Alice is here, she has no idea there's another universe outside. But once she enters, you see, now she has access to the light rays coming from the other universe, other part of the universe. So now she starts seeing, wow, what's this? So there are two sides. I can see lights from this universe that I came in, but there's something also happening on the other side. What's that? Of course, she cannot go back here because she has to go faster than the speed of light, but she can see all of these things that now suddenly reveal to her. So it's very strange. Again, this Humble diagram shows you how everything works actually here. Suppose that there is Bob 2. He also is Daredevil and falls into the black hole. Like Alice never knew that there's another universe here and never knew that there's a Bob here. Bob also never knew that there's another universe here and never knew that there's an Alice 2 here. But they can meet here, right? So if you fall into the black hole, you see objects from other universe, not only light, but also objects that are fallen into the black hole from other universe. This is quite strange. So now I'll show you two short movies. This is when you fall into the black hole and the whole universe becomes blue shifted. So we are getting closer and closer to the black hole. And you will see, it's a little bit slow here, but you will see that the light is bent around the black hole, falling inside, looking at the outside universe, and everything is now blue shifted. And all those energies is coming through that small sphere towards you. So you're just burned into your forehead or whatever where the light hits. Now imagine we could go back. We can't, but imagine we could go back. This is what we will see. So going back, everything is less and less blue shifted. Now the universe opens up and you see it all around you. Before that, you will see just a point or a small circle. So we're coming back, and this is a black hole, and that's it. The next movie shows how universe actually speeds up. So this is what you will see. And then you see the processes in the universe. When you fall into the black hole, again, your field of view of the universe becomes smaller and smaller. The whole universe becomes like a small ball. And now you see that everything is super fast. Of course, again, you're burnt, but everything is super fast. And you can see most of the history of the universe in the 15 minutes you fall to your death, unfortunately, in the singularity. And fun fact, what I'm presenting here is a non-rotating black hole, all that diagram you saw. But if you fall into a rotating black hole, you can actually see the whole universe, history of the universe. Unbelievable. Everything to your past that you were not born at that time, and everything to your future, all the way. You can see all of that. But again, if you don't burn. Okay, the last thing is about, last few minutes is about quantum gravity. So you have heard about probably quantum gravity. Quantum gravity is a combination of quantum mechanics and gravity. And the idea is that, okay, these singularities are just weird. They are infinities. They shouldn't happen in physics. They represent a failure of general relativity or gravity theory. If you combine it with quantum theory, those will go away. So what happens there? In quantum gravity, we just say that we basically combine these two. Suppose that I have a black hole, space-time, and white hole on top, black hole and white hole at the bottom. We join them, and those singularities just go away and are replaced by some transition surfaces. Now it's becoming super weird. I mean, as if it wasn't before, now it's even more. So we have black hole, white hole, black hole, white hole, all the way. So we have one exterior, so like infinite universes outside, 1, 2, 3, 4, and all the way up, right? And these surfaces that were singularities are now transition surfaces, just from black hole to white hole, black hole to white hole. And then you're free to just, play this game of going from black hole to white hole, exterior 1, black hole, that hole, exterior 2. So you just meet new friends in different universes. Hopefully they're friends. And so you can also go to the other part. But all of that is nice, but it shows in our universe, what we see is that there are no white holes. So what happens in reality, apparently, as far as we know, is that actually half of this diagram, unfortunately, is true. So there is no white hole. So that part of the white hole that was disappearing before, now it presents to us again. This white hole horizons go away. The singularity, the left and all the left things go away. The singularity of the white hole goes away. Half of the singularity of the black hole goes away. And voila, this is actually what happens in our universe, apparently, as far as we know. No different weird exteriors, no white hole, nothing. It's just one humble black hole and one exterior outside. So you can all either stay outside and go from minus infinity in time to all the way to future, not falling to the black hole, or you can just choose, to fall into the black hole and just end up in the singularity. So these are all called Penrose diagrams. This is the diagram of black hole that you just search Penrose diagram on the internet, immediately this thing shows up. Now you know how to interpret them and read them. A few slides. This is a work very recently we did with one of the colleagues in the University of Alberta, Douglas Gingrich, and 3 of my PhD students, Federica Fragomeno, Samantha Hergat, and Evan Viennu. And we actually discovered a new black hole, right? And this black hole doesn't have any singularity, but doesn't have any other strange stuff. So what happens is that just that singularity goes away, and inside is like outside. So you just fall in here, you fall in, and there is a whole universe here that you can go on and on and on. Nothing happens to you. So basically, inside the black hole is another universe without any singularity, without any white hole, without anything. Just really, really, in my opinion, obviously, nice. So this is one of other methods that quantum gravity solve these singularities, but gives us some boring maybe things. Again, you can stay outside or go inside and go forever, but nothing really happens to you. Just to give you a idea of how black holes in the universe, there are supermassive black holes that compared to solar system, this is the solar system, all the way to Neptune, sorry, Pluto, all the way to Neptune is like that. But look at the size of this black hole. If you fall in, it takes so long. I mean, there's just so much distance you have to travel to reach to the singularity and everything. So just to mention this, I really rarely read science fiction books. And the reason is that the universe is so much more weirder than any science fiction you ever read. So with that, I welcome you to our universe, and thank you very much.
Okay, thank you. I think we have time just for a couple of questions. So if anybody has any questions, anyone online, you can just unmute your microphone. All right.
I want to take you back to the magic ball that Alice had. It conjured conjures up the ability to perhaps travel faster than the speed of light, but we never know about it. We could call it something like dark energy or something. Is that a possibility?
So as far as we know, we can have objects that go faster than the speed of light and objects that are slower than the speed of light. The problem is that, or the thing that universe tells us is that you can never pass the bridge between these two. If you're going faster than the speed of light, you're always going faster than the speed of light. And the slower also. You cannot go from one to the other one. That's the premise of relativity. There's no way to do that unless we find a new theory that tells us that yes, it's possible. But until now, we are sure that all the experimental evidence tells you that no, it's not possible.
Is that maybe why we'll never find dark energy?
Dark energy is different. Dark energy is the energy of a space-time. Most of people think about this. And it's really not related that much to the speed of objects. It's just the space-time itself is like a fluid, if you want. And that fluid has some energy. We don't know yet. It's just, you know, some of us are thinking like that. But yeah, it's serious.
All right. Anyone else? No? Oh.
Yeah, when you showed the diagram where there was a wormhole between those two universes, is that what a wormhole is? It's connecting two kind of alternate universes, or is it possible, like in science fiction, where a wormhole can lead to one place in our universe to another quadrant of the galaxy or something like that?
Yes. So there are really two types of wormholes. The wormhole I showed you here is basically connecting the white hole to the black hole. But there's another type of wormhole that actually, yes, connects exterior 1 to the exterior 2, two different types of universe. The thing is that for now, just with theories that we know, classical general relativity and gravity, you cannot keep it open with any object. You need to keep it open, right? With some energy, and that energy needs to be negative. We don't have negative energy, so it doesn't make sense. Unless quantum gravity tells us that, oh, there's some way to do that. Even space-time itself at some really high curvature places has negative energy itself, so it keeps open itself.
Okay. Anyone online? Can just unmute your mic. Okay. Anyone else? One more? We have time for one more.
Do stars become eventually black holes, or do galaxies, and how does that work?
So the best person to ask those are astrophysicists. I'm more like quantum gravity theory. But some of the stars, yes, depending on their masses, they become black holes if they're above some threshold of mass, but some of them don't. For example, sun doesn't become a black hole. They need a certain amount of mass. Universe is full of black holes, actually, that we have observed until now. There are so many black holes in the universe that we couldn't imagine before.
Okay. Well, I think that's our time. So once again, let's thank Dr. Rastgoo for showing up. Very much appreciated. All right. You can watch me fumble around here for a minute. So maybe not. We have a few announcements to make. And I will start. This mouse seems to be radical here. Okay. So we have a few announcements, and we're going to start here with Mr. Martins and the Planeway project.
Good evening. Thanks for the talk on black holes. I feel like I'm in one. The proposal that we're putting forward is a proposal to move the black hole. Stuck in my mind. To move the plane wave, the CDK-17, out to Black Nugget Lake. And that's the what. The why is very important. Our mandate is to assist people in learning about the universe, encouraging people to learn about the universe, encouraging education about the universe. And at the moment, people, us included, have a limited access to the facilities to do that. like everywhere else, we have a limited access, but we have the option of increasing the access to people, to ourselves, the access of students, high school and university students, to actual good quality data that they can get on demand. The plane wave is a very high quality imaging instrument. At the moment, it's in our Royal Astronomical Society of Canada observatory here at Telus World of Science. It's in a light polluted environment. It's in the middle of a city where you get a lot of interference from atmospherics. So it's not being used for that intent. If it were out at Black Nugget Lake, it would be in a far darker environment. It wouldn't have the atmospherics from the cities or the light pollution. And it would be used as an imaging instrument, which is its original purpose. So what we're suggesting is that if we move it out to Black Nugget Lake, we would have to build an observatory, put a dome on it, but operate it robotically, which means no one would have to be there to push any buttons. At a certain point, we would get to that point where someone on the internet would operate the telescope, would receive orders for data. We're in discussions as to how that would happen. But it would serve the interests of high school, university students who are doing research. Some professional astronomers would be able to get access to our data, and we would have access to this data on request. So the mechanism for getting that is under discussion, but we're asking for the membership here to approve the project so we can get underway, provide data to students, provide data to ourselves, and move the activities of our center forward. Get our meet our mandate in a better fashion and improve lives for all of us. So the project is described in Stardust this month. The documentation is online. There's a link to it on the Stardust article, and it'll be there for the month of November. So please read it, find out what you think about it, and there will be a membership vote next month in the December regular meeting of our center. So thank you.
Do you want to go through any of the slides at all? Okay. All right. Thank you, Kent. Looking forward to that. All right. We have just another presentation. And I will call up Luca Vanzella. Yep, I'll start at the next one.
Good evening, everyone. I've got two brief presentations for you. One is a little update on Black Nugget Lake Observatory itself, and then I'll talk about a second proposal that's also documented in Stardust. I just wanted to update the membership about happenings at BNLO over what essentially is our first full year of operations. The first light at Northern Prairie, or first light at Black Nugget Lake Not clicking. Anyway, first light of the Black Nugget Lake Observatory was at the Northern Prairie Star Party in September 23, and we've just had another star party in 24, and so we've basically passed our first year, full year of operation. So a lot of activities over that year, and things have settled down into an observatory facility that runs quite smoothly. I'll show you a list in a minute, but scroll it. Okay. We've managed to stage 12 events over the first 13, 14 months or so out at Black Nugget Lake. Some of them centered around the Northern Prairie Star Party and others in other months. And 21 members have stepped up to get the BNLO operator authorization, which I'll talk about a little bit later. And I also want to talk to you about a new BNLO authorization that has just recently been implemented. So a lot of activities have happened over the past year, and here's the list of BNLO events that we've tried to stage, mostly successful. We're dependent on many things. We really only have full access outside the camping period. Northern Prairie has a full booking of the northern site, so we can do activities there. And then our society period, which starts in October and goes till April, is when we have access without worrying about camping arrangements. There, of course, we have the skies are darker earlier, but the weather does change, and so weather is the other conspiring factor. So you can see over here between August of 23, when we first installed the telescope, up until October the 5th this year, we've tried to stage 16 events, and some of them have had to be canceled. Some of them due to the weather becoming a problem on the day of the event, or in one case, lack of people to be able to do it. And we had technical issues on one of the evenings at Northern Prairie, which has since been completely resolved. And so we've had mostly successful attendance at these events, observing events through the 32-inch telescope. You can see the number of attendees is quite healthy attendance at these events. We've had a mixture of public events and member events outside of the Northern Prairie Star Party. One of the early ones back in January was what we're calling a private event, because it really wasn't advertised, but the Canberra Scouting Group asked a couple of our members if they could bring the group out to have a few hours going through. So that's what we're trying to do, and this would be a typical year going forward of the type of events. So we have people monitoring each month of the society period from October to April, and they monitor weather conditions. And then if the conditions seem right for an event, that's when we advertise to the membership about an opportunity. And the most recent one you would have had an email for was on October the 5th, where we had about 40 people come on a very, very nice Saturday evening on mild conditions before the cloudy month of November stepped in. So now we're into the cloudy month, so it's going to be a while. But as things settle down weather-wise, in terms of the late fall, then we should be able to get more opportunities. So about once a month on every lunation is about when we try to have an event out there. So we have. I just wanted to talk to you about the BNLO authorization. So when we first operate, what did you do? When we first opened up shared it. I don't know. Oh, okay. Well, when we first opened up the observatory, we came up with an authorization called BNLO operator. And the three key points about BNLO operator is access, operate, and volunteer. So there's access to a dark site. There is the ability to be on a path to be able to operate the equipment out there, like the 32-inch telescope. Or the Barry Arnold Memorial Telescope, the 18-inch Dob, and then there's the commitment to do some volunteering out there to help with running of events. We can't have events out there without volunteer effort, and also to help in the maintenance and upkeep, as well as evolution of the facility itself. Recently, at Council's direction, we've implemented a second authorization called BNL user, and the key there is access to the dark site without the requirement to be in a path to be able to operate equipment within the facility or necessarily to volunteer. So if anybody's interested in any of these authorizations, all you have to do is go to the website, click on the members area, which will take you to the portal, which has members only information, and you click on the BNLO tab, and you can read about the history of the facility. You can read about the operations of it. You can read about how to get to the authorizations. So that's all you have to do. And I will be here at the break and at the end of the meeting if anybody has questions. There's a few other operators around here that I see in the audience, but if you see me and you have any questions at all about any aspect of the facility or of how to get authorized to get out there, especially now that we are in the society period, you can come see me, or you can go to the members area and read about it, and then you can click the email that's in there to find out, which will send us an email if you have questions that you want to pose in writing. That's it for this.
Thank you, Luca. All right, so Luca has just another quick presentation here. That's the right one. Is that it?
There's a second money motion in this month's Stardust, and it's related to the PlaneWave project that Kent just described to you, although it has independent features. And so there's the money motion that, as it appears in Stardust, which will be up for consideration at the December meeting. It's to spend up to $4,300 from the casino account to basically implement internet access at the facility and install monitoring devices. And so the basics of it is that we would like to install monitoring devices to enable us to enhance security, monitoring, and maintenance of the facility. In terms of monitoring, one of the big conditions is the snow conditions, especially with the rotation with the automation goals of the PlaneWave dome. It'll be important to be able to monitor snow conditions on the tops of the facilities. It also helps to know about snow conditions on the ground, so then we can decide whether or not we need to call in the Beaver County contractors to grade the site for us, because it does get difficult to drive in there if we don't ever clear the snow. In terms of maintenance, internet access will help us. On occasion, we've had to do work on the 32-inch telescope that required communication with the vendor of the control system. And the interior of the Black-Naked Lake Observatory dome at the moment is a Faraday cage. It's not only an observatory, it's also a Faraday cage. Your devices do not work very well if they depend on wireless connectivity on your phone plan. So it's very difficult to have the vendor online on trying to resolve a couple of commissioning issues with the telescope, as well as having internet access. It would help us with the installation of some of the equipment, enhance security. Another thing it does is, if we want to move towards any kind of reach out from the observatory out in terms of public outreach without a physical presence, that would enable it. At the moment, in order to enjoy BNLO, you have to be there. There are other ways to be able to participate if in fact there was internet access. Those are independent of the other proposal, but if in fact the PlaneWave Observatory is approved to proceed, remote operation or robotic operation is simply not possible with internet access, without internet access, so that would be a requirement. The other thing that it opens up, which you'll read about in the PlaneWave proposal, is that if there's a desire, we can collaborate on astronomy networks on research or citizen science initiatives like the Backyard Astronomy Network and others that are listed in the proposal. So those are the main benefits and things that can be done with BNLO. So we're looking at the main components would be internet access. So the main provider out there is MCSnet. You can see there's BNLO with a red dot, and that's their coverage area. It's used by Beaver County. It's also used by the golf course across the way and the campground operator. And some of our own members actually use it, and they're quite a good quite a good vendor. One of their programs, which I'm hoping that we can get, we can make an application for at some point in the future, is that they have a community support program, and there are ways to reduce the internet fees all the way down to zero, depending on the type of nonprofit activity that you're engaging in. So that's a future, but for now, we'd have to start by paying for it. Weather monitoring system would be based on this commercial package called Sky Alert, which allows you to have a weather system dashboard that you can access remotely. Surveillance cameras, typical surveillance cameras, and an all-sky camera would be another acquisition. And Jay Lavender has kindly offered to build the all-sky camera for installation out there, but he will need, there will be some funds required for the parts. But the vendor for the all-sky camera is Jay Lavender. So you'll see there's a brief, the budget comes out to this, and that's why it roughs out to about $4,300. So now again, that'll be the money motion on the table. And as Kent pointed out, both money motions are listed in on page 5 of Stardust, and they both have a link to the members area where you can read the full detailed proposals. And so we'll talk about it again next month, but everybody can now consider it over the next month. Thank you very much.
All right. Thank you, Luca. All right. So just if anybody is wondering, the council is allowed to approve expenditures up to $1,500, and any other expenditure greater than that has to be presented to the membership for voting. And that process starts by publishing in the Stardust for 30 days first, so that the membership is completely informed on the expenditure proposal. And so it's in the November Stardust, and we will put both expenditure proposals to membership vote at the December regular meeting. So if you'd like a part in that, come to the December meeting. Okay. We have 2 more points and then we'll break. So I would like to ask Doug Hube and Alistair Ling to please come up.
This evening, we are able to complete an exercise that began last May. All the pieces are in place, make an important award. As you know, the National Society offers a number of awards every year. Service Award, for example, which a number of us hold. But one of perhaps the most important award that the RASC offers is the Chant Medal. The Chant Medal was introduced in 1940, 84 years ago, and named in honor of C.A. Chant, who served in a number of important positions in the early decades of the society. It is a prestigious award that has only been offered during those 84 years 30 times, and only 2 of those awardees were members of the Edmonton Centre. The award, a new award was announced at the GA earlier this year, fortunately to a well-deserving member of our centre. So I would like to call Warren Finley to the stage to receive the Chant Medal for 2024 for his outstanding contributions to amateur astronomy. And as you know, many of the activities that Warren has been involved in are really on the level of professional contributions. We're very proud to make the award on behalf of National Council Chant Medal for 2024 to Dr. Warren Finley. Well done. Thank you.
One of the things I'd just like to say in additional to the congratulations is to really try and put into words the admiration and just sort of blowing my mind as to the amount of effort it takes. As many of you know from through the stuff that I do, that I'm pretty keen, and Horn's level of keenness is quite literally sort of Olympian scale above what I do. I do a lot. Anybody, an amateur athlete out there does a lot, but that Olympian scale, and that's one of the things that Warren has really done with the observing over the last, decades, is that perseverance that one sees in the Olympian athletes. So my admiration and respect. Well done.
Thank you very much. I didn't know this was, happening how you had said something about it, but thanks so much for pursuing this. I know it took a while to finally get the medal here, so I appreciate the efforts. Perhaps not Olympian, but definitely some effort went in on your two parts. So thanks so much for nominating you two. And I just like to thank the RASC and all its members over the years for supporting me in the sometimes rather crazy things that I've done, and being there, all the teams I've worked with Black Nugget Lake, and I'd just like to say that many of you inspire me, and many of the things I've done have come from inspiration from other club members. So I'd like to just thank the club and the RSC members for the support over all the years in achieving what I have achieved here. So thanks so much.
What an accomplishment, really. Okay, our final announcement is Mr. Chris Meerveld. Talk about the Jasper Dark Sky Festival this year.
Thank you, Jay. Last time I was up here, I said that the Jasper Dark Sky had been canceled for the year, and everybody knows why. There was quite a disaster there. But shortly after that, about 3 weeks later, they called and said, "Do you think you can still set something up?" And I said, "Well, we can certainly try." And they said it's more of a healing event. And I guess most of us misunderstood what they meant by that, because we thought they meant, have people from the town look through our scopes. That's not what they meant at all. What they meant was that they wanted us to be first in line to have the first event back after the disaster and make some sort of normalcy about the town again, because it is a disaster. They said just to send a few people. We don't have a large budget. So we got 4 couples, which included myself and my wife, as well as Dave and Carol, Susan and Rick, and John and Secrete. And those were chosen because they both had solar equipment and night equipment, and they are well versed with that event. And we needed somebody that, or some people that could fill in quite quickly. So we had it a week ago in Jasper. The first thing my wife and I did was take a tour of the town just to take a look at it, because they said it was supposed to be a healing event, to see what it was like. And it is rubble in so many areas of the town. And all around the town for many, many miles, you see nothing but these black toothpicks. All the foliage is off the trees. And it's going to take a long time to get back into shape. To see it, I wanted to read a little part from an email that I got from the organizers after we did the event. It said, "Thank you very much for coming out this past weekend. Your presence created some much needed normalcy in a place that is nothing but normal right now. I wrote back, I appreciate your comment about some much needed normalcy. Over the years, we have, my wife and I have developed a favorite breakfast place. When we walked in this time, our favorite waitress teared up and gave both Monica and I a big hug. She said she was really hoping we were coming. She meant the RASC was coming. During the course of chatting with her, she sobbed a few times as she was telling her story. We didn't ask any personal questions, but she just needed to tell someone. And she was very happy that we came as a group. So when they called it a healing event, that really brought it home to us that it was a healing event. And we were honored to be the first people or the first event out there of the season after the disaster. We, as I said, we had four couples go out. We had a bad scene as far as the weather was concerned. We didn't get any night viewing except maybe 2 minutes of Saturn for the 2 nights we were out there. And the solar viewing, we had a little bit of success, but not as much as we normally did. But we did a lot of show and tell. And as you can see by the comments from the organizer, it was very much appreciated that we did go out. Normally they pay us $1,000 for coming out there. We forewent that this year because their budgets are shot. They depend on tourism, and obviously there is very little tourism this year. Thank you.
All right. Thank you, Chris. And just to mention too, a very short notice, it went from JDSF was not happening to it is happening. So kudos to the JDSF committee for pulling those volunteers and to the volunteers for putting their best foot forward in a pretty tough time. Okay, we will break just shortly if we can. And before we do that, in the spirit of our guest speaker tonight, I have astronomical trivia that I will leave on the screen. And that is, what is the term for the theoretical ring-like structure surrounding a rotating black hole, where objects can remain in stable orbits without falling into the black hole? So that's your astronomy trivia before the break. So we'll break for, how about just 10 minutes so we don't go too late? And we'll come back about just before 9:15. All right. Once again, thank you to Joanne. It's always right on the spot. So thank you, Joanne. Okay, we'll go through the last half here, try to keep on time the best that we can. So I'll just quickly go through this month in history. So I thought there's a few interesting ones here. 1833, the Leonid meteor shower was well, I guess they call it the meteor storm, was one of the most spectacular meteor displays in recorded history, with an estimated tens of thousands of meteors per hour. I heard it was over 20 a second. And the event sparked widespread interest in meteor science and is considered one of the key moments in the study of meteor showers. And I'm guessing also in the fear of meteor showers. November 1924, Edwin Hubble confirmed that the Andromeda Nebula was not a gas cloud within the Milky Way, but a separate galaxy altogether. Using the 100-inch Hooker telescope at Mount Wilson, he observed the Cepheid variable stars in Andromeda, calculating the distance and proving that it was outside of the Milky Way. That was actually 100 years ago this month. And I'm sure to Jeff's liking here, November 8th, 73, Pioneer 11 made its closest approach to Jupiter, coming within 34,000 kilometers of the gas giant. It provided the first close-up of images of Jupiter and discovered the intense radiation belts and polar regions, as well as identifying presence of its massive magnetic field. So that is this month in history. Okay, moving on. Book of the month, Mr. Zelchik.
Sure. Good evening. Greetings from the Lamplighter Library, from co-librarians Berta Beltran and myself. The library is located just off the main entrance here. It's open before, in the middle, and after the meetings. We acquire new books, and also we acquire a lot of books that are donations from members. This month's book of the month is A New Acquisition Before the Big Bang by Laura Marcina Houghton. What came before the Big Bang and what exists outside the universe it created? Until recently, scientists could only guess at what lay past the edge of space-time. However, as pioneering theoretical physicist Laura Marcina Houghton explains, new scientific tools are now giving us the ability to peer beyond the limits of our universe and to test our theories about what is there. And what we are finding is upending everything we thought we knew about the cosmos and our place in it. Marcina Houghton is no stranger to boundaries or to pushing through them. As a child growing up in communist Albania, she discovered a universe beyond her walled-off world that through the study of math and science and through music. As a female cosmologist in a male-dominated field, she transcended the limits that society and her profession tried to place on her. And as a trailblazing researcher, she helped to revolutionize the study of our universe by revealing that, far from living in a cosmic Albania with a world that ends at its borders, we are part of a larger family of universes, a multiverse that holds wonders we are only beginning to unlock. Marcina Houghton's groundbreaking research suggests that we sit in a quantum landscape whose peaks and valleys hide a multitude of other universes and even hold the secret to the origins of existence itself. Recent evidence has revealed the signatures of such sibling universes in our own night sky, confirming Marcina Houghton's theoretical work and offering humbling evidence that our universe is just one member of an unending cosmic family. The incredible saga of one scientist's mind-expanding journey through the multiverse before the Big Bang will reshape our understanding of humanity's place in the unfathomable vastness of the cosmos. So this book came out very recently, and it's available after the meeting. So thank you very much.
Thank you, Mark. And we do have a link up there. If you're ever interested in what the book of the month is, you can just go to our website and click on the library at the bottom of the page. Okay, I will ask Dave Mussel to come up. Abdur is not available tonight for our Astro Imaging Corner, so Dave did such a good job last time. We're asking him back.
Good evening, everybody. I'm Dave Mussel, and I'm standing in for Abdur tonight, who couldn't be part of the meeting tonight just because of personal commitments. Just make sure this works. Perfect. Yeah, so we have another trove of amazing images that have come into the Astro Imaging Corner. And for everybody, those of you who are doing some imaging now, you can go to the website. There's at the bottom of the front page of the website, a link that allows you to post your images via email to Abdur, and he will collect them and produce these slideshows. And he does an amazing job with it. So he put this together and asked me if I would just present it on his behalf. So I'm just going to roll right into it here. So the first one is from Kent Martins. This is the Perseus double cluster. It was shot at NPSP 2024, and it consists of 40 subs culled from a total of 65 altogether, subs meaning subframes or sub-exposures, and processed in PixInsight with darks and flats, and photometric color correction, and blur exterminator and noise exterminator, which are tools that come from RC Astro. And so this is a really lovely image, Kent. Kent had to wait a long time to see these because he sent them to me last month and I neglected to put them up or just forgot to do it. So anyway, Kent, thanks for your patience. And this is another one from Kent. This is M33. And Kent says this is an image that he's been wanting to get for some time. By the way, these are all shot with the QHY 294 MC Pro on an Orion ED80T with a field flattener. This one consists of 33 sub-exposures processed in PixInsight using the blur exterminator and noise exterminator from Russell Croman. This next one is LDN 395, also from NPSP, and again with the QHY 294 MC Pro, and also processed the same way using a blur exterminator and noise exterminator. And a fourth one from Kent, the Pleiades, another gorgeous shot from NPSP as well, 72 sub-exposures with flats and darks done in process in PixInsight, again with the same noise and blur exterminator tools. And this one was done with the stars processed with the rest of the image altogether in the images of M33 and LD N935. He says he split the stars off and processed them separately. He says, I'll have to try that with M45 but I haven't had the chance to take that step yet. So anyway, great job, Kent. These look great. All right, this one comes from Marion Hobbs, and Marion and Ellen were out at Black Nugget Lake and observed this fairly late at night. And so this is what Marion says about it. Interesting auroral display. We've seen many gorgeous pictures of the large auroral storms on October 5th and October 6th and 10th. This is from a quieter night on October 30th at about 5:30 a.m. looking to the west at BNLO. There was normal diffuse greenish light with some rays across the northern horizon, at times reaching about 30 degrees high. I noticed a whiter ray from the west to the north that looked like Steve, or Steve-like. Then a few minutes later, this disappeared. A ray on the right ended nearly due north and hung around for a good while. The rest were short-lived. I thought it looked rather unusual, taken with the Samsung S24 cell phone. And this one's from Alan. This is NGC 7635, also known as the Bubble Nebula, Sharpless 162 or Caldwell 11. This is an H alpha region of emission nebula in the constellation Cassiopeia. It lies close to the open cluster M52. The bubble that you can see here is created by a stellar wind from a massive hot magnitude 8.7 central star, SAO 2575. The astrophoto was taken with Nina on his Celestron Edge HD 8 with the 0.7 reducer and Optolong L-enhanced filter and ZWO ASI 2600 MC camera on Skywatcher EQ6R Pro mount. On October 30th at BNLO, the astrophoto has 12 subs at 300 seconds each, for 16 minutes total exposure time. This is the very familiar Dumbbell Nebula, also known as the Apple Core Nebula. That's the name I like for it. M27 and NGC 6853 is the other name for it. This is a planetary nebula, which is a cloud of nebulosity surrounding a white dwarf in the constellation Vulpeculae, at a distance of about 1,360 light years. This astrophoto was taken with Nina on his Celestron Edge HD 8-inch, which also had the 0.7 focal reducer on it, and the ZWOA ASI 2600 MC camera on his Skywatcher EQ6R Pro on November 2nd at BNLO. The astrophoto has 20 subs at 180 seconds each for 60 minutes total exposure time. And this is the NGC 457, the OWL cluster, which lies some 7,900 light years away from the sun. It has an estimated age of 21 million years. The cluster is sometimes referred to by amateur astronomers as the OWL cluster or ET cluster due to its resemblance to the movie character ET. The astrophoto was taken with Nina, again on his Edge HD with the 0.7 reducer and the ZWO 2600 MC color camera on the Skywatcher EQ6R mount. This was taken on October 30th at the BNLO and consists of 15 subs of 60 seconds each for 15 minutes of total integration time. This image comes from Josephine Christensen. This is M31, and of course the Andromeda Galaxy taken with the C-star in mosaic mode. This is stacked JPEG. This is the stacked JPEG that the C-star provides when it's used. It's 2 hours at 10 seconds for each picture that was taken over the course of that time. It's called framing in the C-star, I guess. I've never used one, so I don't know what that how that operates, but that's interesting. It's a pretty amazing piece of equipment. It was edited in Lightroom on a Samsung phone. That's pretty amazing, Josephine. Just wanted to do simple editing on JPEG with the phone, which it's amazing that we can actually do that now. That she says anybody can really do. I'll do the FIT file. I guess FITS is the format later in serial to compare. Taken on October 30th, 2024, and started just before 8 p.m. and finished at 11:34 p.m. southwest of Edmonton, looking south. Light pollution filter off and cropped. So here's another one from, well, who could that be? This is comment C/2023 A3, Southwest Edmonton in Windermere, taken with the Galaxy S22 Ultra in night mode. And that's another view of the same comment. So this image comes from Hans S. Jans. And this is NGC 7789, taken with his camera, which is also an ASI 2600 MC Pro in RGB from Bortle 7 to 8 skies with a UV IR cut filter. NGC 7789 is the white rose cluster. This was composed from almost 7 hours of data. He says, I also added 100 minutes of H alpha data in case there was any background signal, but not expectedly, there wasn't much at all. It's a beautiful image. And this is M45. Taken with the same camera that he took the last image with, also in RGB from Bortle 7 or 8 skies, and again with the same filter, the UV IR cut filter. About 15 hours of time went into this. You can see a lot of detail in here. This image comes to us from Tom Owen. This is M33. This image was acquired at Pigeon Lake over 4 nights from October 7th to 11th, or 12th, sorry, and using his Takahashi TSA 120 refractor at prime focus at 900 millimeters focal length. This consists of 5-minute, 4-minute, and 3-minute subs, and were taken with the QSI 683 camera using HA or hydrogen alpha luminance, red, green, and blue filters for a total exposure of 6 hours and 21 minutes. It was a battle to get usable sub-exposures because of the aurora and the waxing moon. Quite a few had to be discarded, and processing was also more difficult than usual, he says. Subs were stacked in AstroPixel processor and processed using star tools. He says, I think the HA filter really brings out the reddish clumps of the dusty nebulae around the core. And I would have to agree that you can see a lot of pinkish reddish detail there, which represents that nebulosity that is present in that galaxy. So this is IC 410, also from Tom. This image was reworked from light gathered at Pigeon Lake with Takahashi FS 102 telescope and a QSI 683 camera in November and December of 2021. 17 6-minute subs in H-alpha and oxygen 3, and 35 6-minute subs in S2 or sulfur 2 for a total exposure of 6 hours and 54 minutes. This was restacked using AstroPixel processor, then reprocessed using star tools. Maybe it should be renamed the Blue Grotto Nebula. What do you think? That's what Tom is asking. Beautiful. This image is from Jonathan Porter, and this, of course, is also M45. Here's a picture that I took of the Pleiades from October 29th, 2024. His telescope was a Teleview 85 millimeter refractor with the TRF 2008 0.8 reducer flattener. The effective focal length was 480 millimeters at f5.6, and he used the Canon EOS R mirrorless full frame, not modified. And the location was farmland southeast of Rossland, Alberta, which are Bortle 3 skies. He says here that he got about 3 hours and 22 minutes of total integration time over the course of 120 exposures at ISO 1600, and process it with the Deep Sky Stacker, PixInsight, and Photoshop. Really nicely done, Jonathan. And the next one from him is M42, the Orion Nebula. Here's a picture that I took of the Orion Nebula on October 29th, 2024. The telescope again was the Teleview 85 millimeter APO refractor with the same TRF 2008 0.8 reducer flattener. Again, the effective focal length was 480 millimeters at f5.6, and in the same EOS camera that he used in the previous image, and from the same location as well, near Rossland. And this one is the North American Nebula, NGC 7000, one of my favorite targets. This was from Taha Basharat, and it consists of 35 hours of total data. It was shot off of an HEQ5 mount with Antlia 5-nanometer filters, taken from Bortle 8 skies in his backyard in Edmonton. The next one is from Mark Zalchik. This is the aurora of October 10th and 11th, And at 2241 Mountain Daylight Time with a 50 millimeter lens at f1.8 with 0.3 second exposures at ISO 3200. The fantastic auroral display was already going 2 hours earlier at dusk, and for an hour around 11 p.m. formed a dazzling corona overhead with some fainter flames pulsating for several minutes. That's a great description, Mark. This image is from, this is also from Mark Zalchik as well. And here's an image from Warren Finley, the aurora for this month's Astro Imaging Corner. He says, I've attached an aurora photo taken during the geomagnetic storm on the evening of October 10th. That's an amazing image. It's got some beautiful reflections off the pond and the boat. Beautiful. And this is an image also from Warren. This is the same comet that Josephine imaged. This is comet C 2023 A3 taken on October 13th. And here's one from Stephen Portillo, and you can just barely make out in just above the center the dim view of the comet. I took this photo of, boy, I can't even say this. I'll just say Atlas on October 12th from Gates Pass outside of Tucson, Arizona with my Google Pixel 8 Pro. And here's a shot from Doug Hube. This is solar, he calls it a solar transit, and I think it's beautiful. The sunset on September 18th of this year, handheld Nikon P950 at 1500 millimeters at f6.5, ISO 400, 320th of a second, and the image uses up 3.7 megabytes. And the next one, also from Doug, is a close-up of that. And of that, he says, this is solar transit crop of the previous image, and it reveals a flock of Canada geese, although they could be sandhill cranes. And here's a beautiful shot of the moon, very ghostly and sci-fi looking, also from Doug Hube. 2 days and 23 hours old moon setting on October 5th of 2024, handheld with the Nikon P950 again, 2000 millimeters and f6.3, ISO 800 and 1/100th of a second. It's a really interesting shot. The next one is from Abdur. And this is the dust and gas clouds around Polaris. This is a view that I have never seen before, so I think this is quite amazing. This is a rarely imaged integrated flux nebula around Polaris. The region is full of dust and gas, and the image was taken with a Rokinon 135 f2 lens on a camera, a Canon 6D DSLR, which is unmodified. And it's on an MSM Nomad star tracker. 11 hours from Black Nugget Lake, a dark site processed in PixInsight. And the final image for tonight is this one of the same comet we've been seeing, comet C 2024, I think it should be, A3, imaged with his ASCAR 60 millimeter refractor. A little bit of green is visible at the front of the comet. You might not be able to see it in this projection, but on the slides, you can actually see that. The camera was the ASI 2600 MCD with the UV-IR filter. The D stands for the dual, I believe. So it's a camera that does both auto-guiding and imaging. 1 hour and 21 minutes of exposure time from a dark site on October 29th, 2024, processed in PixInsight. So quite a haul of amazing images again this month. Thank you very much to all the imagers who are out there taking shots and submitting them to Astro Imaging Corner. This is one of the highlights of our meeting every time. And keep up the great work.
Great. Thank you, Dave. And thanks to everyone who submitted. Keep those pictures coming. All right. Okay. We'll just go through our astronomical trivia. So the challenge was, what is the term for the theoretical ring-like structure surrounding and rotating black hole, a rotating black hole, where objects can remain in stable orbits without falling into the black hole? And I can tell you it is not the event horizon. Does anybody know what it is?
Ergosphere.
Oh, ergosphere is correct. I had never heard of that before. A region outside the event horizon of a rotating black hole where objects can gain energy and orbit due to frame dragging. Who knew? And you can read more about frame dragging on the internet. How's that? But anyway, I learned something today. Okay, final announcements. So again, Mark and Berta are doing some work cataloging books, that sort of thing in the library. And so if you're interested in helping out, please send them an email, and their contact info is on our website. Don't forget about this Astrospheric software that we have for our members. It's a great forecasting tool for weather, cloud cover, smoke, all that sort of thing. It's really quite good. And if you're a member of the RASC Edmonton Center, you can send me an email, and I will subscribe you to the application. So just a note that you have to use the email that's associated with your RASC membership. Quick reminder that council elections, so every 2 years, we elect a new council slate, and that is this January 2025. So if you are interested in helping run the organization, then please consider a seat on council. I published all the positions and seats and that in the Stardust this month. So again, if you are interested, send me an email. It's a pretty worthy role. Upcoming events. So observers meeting hosted by John Stolte and or Berta Beltran, and that's this November 13th at 7:30. It's online. What's up over Edmonton for November was the dates, just the way they worked out, was actually held on October 30th, but you can go to the Edmonton Center YouTube channel to view Jeff's What's Up. It's always very informative and very entertaining. And our final meeting of the year is this December 9th at 7:30 right here. So if we have nobody else, no other announcements, anyone going once, going twice? All right, then I will call the meeting adjourned, and thank you everyone for coming out tonight.